Our last technique is series, in particular power series. And so we want to look at this idea. So this first video is just the main techniques we need to use with these power series. So for instance, if I define a function y of x, I'm going to do it as some a0 plus a1x plus a2x squared plus a3x cubed plus, and just keep going. And so this is like a Taylor series, but it's not as specific. Now this is centered at 0. We can also center at a different number, but for the moment we'll just have it centered at 0. You can review Taylor series to kind of look at this. Now it's going to be much more convenient most of the time to use a sum, so we'll say k equals 0 to infinity, and so you see we have a sub k x to the k. And so when k is 0, I get a0 x to the 0, so that's just a0. Then when k is 1, so plus a1 x to the 1, and then a2 x to the 2, and so forth, and we add those all up. So that's our series. Now the first thing we want to be able to do is when we take the derivative, so we need to know how to take derivatives. Well, if I look at that top part, I'll get a 0 because a0 is a constant, and then a1 plus 2a2x plus 3a3x squared plus 4a4x cubed. Now, if I just use my summation notation here, it's the same idea. I'm just bringing the k down and leaving the exponent k minus 1, so I could write that as k equals 0 to infinity of ak times, and now I'll put the k here instead of in front. So ak times k x to the k minus 1. Now, technically that's correct, because notice when I have k equals 0, I'll get a0 times 0, so I'll get a 0 just like I did before. But since that first term is 0, I don't actually need it, so I could just start my summation at k equals 1 to infinity a sub k to times x to the k minus 1. Alright, and then we take, we'll just do the second derivative, but of course we could keep on going. But in this class, since pretty much we stopped at problems with two derivatives, second order problems, this will be enough. So take the next derivative. Well, I would still have that 0, but then I would get that 0 plus 2a2 plus 3 times 2 a3 x to the 1 plus 4 times 3, or 12, a sub 4 x squared plus dot dot dot. And so you see, if we started up here at this row, right, that's k equals 0 to infinity ak times k minus 1 x to the k minus 2. Now in this case, the first two terms are 0, because when k equals 0, I get 0. When k equals 1, well, I get 1 minus 1, so I get 0. And so, we could just not have it start at 0, which is typically what you will see. So a sub k, k minus 1, x to the k minus 2. Okay, so that's taking derivatives. Oh, I'm not sure what I just did there. Whoa, I don't know. Not sure why it. What if I do that? Aha! There we go. So then, okay, so we know how to take derivatives. Piece of cake. Now the other thing we need to be able to do is add a couple of these series together, because you see, if I had something like y prime minus 2y, that sort of expression, well, according to our series, well, y double prime I have right here in front of me, so that's the sum k equals 2 to infinity, a sub k, k minus 1, x, k minus 2, and then minus 2 times the sum in the original series was k equals 0 to infinity, a sub k, x to the k. So you see, well, this is great. I can just add these things together. Well, except the easy way to add them, I really need these exponents to look the same. See, that's a k minus 2, that's a k. So let's take an aside. I'm going to do a new page here just to kind of show. So just suppose I'm trying to add, k equals 0 to infinity of some a sub k x to the k, and I want to add to that some sum k equals 0 to infinity b sub k x to the k. Well, I've got like terms here, right? As you add these together, I have a x to the k, x to the k, they both start here at 0. And so if I have a situation like that, I simply take k equals 0 to infinity, combine the terms, so I have an ak using the distributive property, right? And I get that. So that's a piece of cake. Now, if you don't quite believe me, well, the way we'd have to know these converge. If they don't converge, well, this makes no sense anyway because they don't converge. But as long as they converge, then we can rearrange our notation and so forth. So if you think of partial sums, we started with some a0 plus a1x plus a2x squared plus a3 x cubed. So suppose we only went up to the 3, then b0 plus b1x plus b2x squared plus b3x cubed. Then when I add those together, right, I could put the a0 plus b0 together. Then the x terms, I have a1 plus b1 x, and then plus a2 plus b2 x, and same thing, a3 plus b3 x cubed. Oops, x squared. Okay, so that's the... Get the pen too close to the bottom or something and it scrolls like that. Haven't been able to not do it, so I'm just an inferior human being that way, I guess. So okay, so that's the idea. So we can add the series like this very simply as long as the powers on k match up, and I start the series at the same place, the k equals 0 and so forth. So the problem is what we're going to have is we're going to need to add stuff like, k equals 0 to infinity, a sub k x to the k, and then something else where I'm just going to write it very generally this time. So k equals 2, say, to infinity, b sub k x to the k minus 2, something like that. Well, we have to get those exponents to match, and usually what I do is I try to make them all k's as opposed to all k minus 2's. But, technically I could make them all k minus 1's. I could, I could go to k plus 5 if I wanted, but they have to be the same. And so what I'm going to do is I'm going to change this one to be x to the k. Well, so what I want is, but it'll confuse me if I just call it k. So I'm actually going to make a substitution here. I'm going to let j be the k minus 2. Now, I also find it helpful if I then solve for k and I have k equals j plus 2, because then whatever's easier to sub into, I do that. And so now this expression that I had up here is k equals 0 to infinity, a sub k x to the k. Now I can change all those to j's, but actually I'll change the j's probably back to k's once I get done, but in that case it'll just be by name only, plus the sum. Now, so k started at 2, but if k is 2, I get 2 minus 2 is 0, so j equals 0. When I get up to infinity, well, infinity, in other words, if this goes off to infinity, if I subtract 2, it still goes off to infinity, so I have j equals 0 to infinity. The k, this is where it's kind of nice to get the j plus 2 in there. So see, I have b sub j plus 2, and then x, well, j is k minus 2, so that's j. So see, now, actually in this particular case, these both match up very nicely. So k equals 0 to infinity, a sub k x to the k, and then, probably it's best to rewrite these all as the same letter. I could have picked j, I could have picked k, I could have picked some third letter. It's kind of like what I tell people when they get married. I always think people should pick the same last name when they get married. I don't care if it's his name, her name, or some other name that they agree on. I just think it's easier. It's my little soapbox for that. But so now that I have this, you see, I can write this as the sum k equals 0 to infinity, and because they started both at the same index, a sub k plus b sub k plus 2, like that, and x to the k. Okay, so that's the idea. Let's go back to what we had here. All right, so we need to do the same thing here. You see I've got a k minus 2 up there, and so I'm going to do that same thing of I'm going to let j be k minus 2, but that means k is j plus 2. And so this thing becomes the sum. Well, k started at 2, but if k was 2, then j was 0. J equals 0 to infinity again. A sub k, so that's a sub j plus 2. K, well, that's j plus 2. K minus 1, well, that's j plus 2 minus 1, so that's j plus 1, and then x to the j, and then minus, and I'm going to put the 2 inside there, so this is the sum k equals 0 to infinity of 2ak x to the k. So now, this is just dandy. I have the sum, and in this case I'm just going to pretend all these j's are k's, so I'll have k equals 0 to infinity. That's a k plus 2, k plus 2, k, oops, that's 2, k plus 2, k plus 1, and then minus 2ak, and then times x to the k. So you get this very complex looking coefficient, but nonetheless, that's what it is. You know, so it's just that. I just had to get everything lined up so I could add it together. All right, so we have that. Now let's go. We don't have much more room there, so I'll add one more page. Another possibility you could have is that even after you do a substitution, you know, what do you do if you have something like k equals 0 to infinity of x to the k, and then plus a sum. Say you've done some work, but it turns out you've got k equals 1 to infinity of some, you know, b sub k, and now you've got x to the k. No big deal. Just write that first term of this one separately, so you have a0 x to the 0, or 1, then plus the sum k equals 1 to infinity of a sub k x, so this is all equal, x to the k, and then plus the sum k equals 1 to infinity b sub k x to the k. And so this is a0 plus the sum k equals 1 to infinity of a sub k plus b sub k, all times x to the k. So, you know, if the indices don't start at the same place like these didn't, we'll just knock off the first few of whichever one has the lower indices, and then go from there. Okay, so this is the basic idea of what we're going to need to do with these series. So power series, we can take derivatives, and then once we have those derivatives, we could substitute them into an expression like this, and then get the exponents to match up on the x's, so that's what we need to do first. And then once we have the exponents match up, if the indices, as far as where we start and count by, so these were counting by ones and starting at 0, then we can just put together like terms. If the indices don't match, like we had here, in this case, just get rid of those, you know, or well, write separately those first few indices until you can get the indices to match. Okay, so that's an introduction to what we're going to be doing with these series.